So now we're going to calculate a couple other things. First, we're going to calculate our an, which are this, and bn. All right, so what is the definition of an? So I'm just going to simply write the formulas. It's 2 over t. I need a lot of space. It's t f over f of t cos 2 pi n f0 t dt. This is just a definition. So this is a definition, or you can say a formula, right? So I'm gonna take my signal, which is 2 over t. So this is just a definition. Now I'm plugging in the actual value. I have a period of this from negative t over 4 all the way up to t over 4. My signal f of t is a, and this is a cosine 2 pi n f0 t dt. All right, so far so good. All right, there's something else. When I am doing integration, when I have borders which are symmetric, which means on this side I have 0 to t over 4. All right, from here to here, you're going, the distance between what the signal that I'm trying to find area under the curve of is symmetric, isn't it? Aren't they symmetric? We're going to same distance from 0 to t over 4. It's just like saying I'm going from negative t over 4 all the way up to 0. If that is true, if I'm doing integration symmetric borders, so basically I can do this. I can change this. I can change this into this. So this would become from 0 to t over 4. My integration limit will change from 0 to over 4. And I'm going to just simply make that replacement. I'm going to multiply. So basically what I'm doing is this. I am calculating only one and I'm multiplying the answer of that, whatever the answer I will get, by 2. So this is actually going to be 2 times 2. I hope you're understanding what I'm trying to say. When I have borders which are symmetric like this, I'm going from 0 to t over 4, same distance, negative t over 4 to all the way up to 0, same distance. So when I have symmetric borders, what I can do is this. I can change my integration limit from t to 0 to t over 4. All right, and I can multiply whatever the thing I will get by 2. So this would become 2 times 2 is 4 over t, and this is just nothing but a constant. I can bring that constant out. So this would become 4a over t. Now the rest of the thing is just simple, cos 2 pi n f0 t dt. I hope you're getting it. All right, so the next step is going to be this. So the next step is 4a over t. This is that. How do I get this 4? I hope you're getting it. When I change the limit, and if I have symmetric borders, I'm going from 0 to e over 4, multiply this 2, which was outside, which was part of the formula, with 2, I'll get 4, and then I'll brought that for a out. Now, here's the thing. What would be the integration of this? The integration for this, guy, is just going to be simple. It's going to be sine 2 pi n f0 t divided by that inside kernel, which is 2 pi n f0. All right, this is going to be sine of this whole thing. It's just not sine of t. It got some inside kernel too. It's just like saying sine of a times x. All right, so when I take an integration, it will be sine 2 pi n f naught t divided by 2 pi n f0. Now here I'm going to put my integration limits. I hope you're getting it. I hope you're getting it. All right. So here's how the few things that I'm going to do. First thing I'm going to do it in the next step. So this is going to be 4a. This is t. All right. So that is going to be sine 2 pi n f0 t. There's a reason I'm doing it. And I'm going to change this f naught with 1 over t. So when I do it, 2 pi n 1 over t. So this t and this t would cancel out. All right. I hope you're getting it. I haven't put my integration limit yet. All right. I still need to do it, but this is an extra step that I'm doing. So now this is what I'm doing. And this 2, this would cancel out. So this is 2. So I left with 2 on top. All right. So far I have now 2a n pi sine whole thing 2 pi n 1 over t in place of this. All right, in place of this I have 1 over t, and I'm going to put t multiplied by t over 4. I hope you're getting it. I hope you're getting it. I hope you're getting it. What have I done here? All right. So you know where you got that 2 from. There was on the bottom you have 2 pi. Okay, so that and that would give you that 2. All right. Now I'm putting my integration limits. So that is just n pi, or pi n is just brought underneath 2a, which is this. Sine 2 pi n, f is 1 over t, and my limits is t over 4, minus 0 is just nothing. So this and this would cancel this, and this would be 1 over 2. So this whole thing would turn out to be something really nice, which is going to be 2a n pi. I hope you're seeing this. N pi sine n pi by 2. Right? On the bottom I left with 2 and I left with n pi by 2. This is the value of my an. All right? This is the value of my an. Now, I am running out of paper. Let's quickly bring in and let's calculate my, so this is step number 1. This is step number 2. All right, now we're about to do step number 3. So this is the value of my an. This is the value of my a naught, which is a over 2. Now let's just quickly bring in bn. All right. So far what we have calculated, so far we have a naught, a over 2, an, that is equals to, which we just calculated, an, this is 2a n pi sine n pi by 2. All right. Now we need to calculate bn because bn is also there. So bn, in order for me to calculate bn, here's the formula. All right. Formula is 2 over t is t f of t sine 2 pi n f0 t dt. Okay, so sine of 3 pi by 2 turns out to be -1. So now this whole thing turns out to be -1, isn't it? So this is going to be, so now when I plug in, so a is already out. In place of this, when I plug this value in, this would be what? This would be minus, because this whole thing what we just calculated turns out to be 1, isn't it? -1. And then in place of n, there's a 3, isn't it? We use 3, and n is equals to 3. So this is going to be 1 over 3rd. All we left with this. So when I evaluated this term for 3 as being in place of n, that is just -1. So -1, 2a and pi, which is common. So we have taken that out. But in place of n, we have -1/3, which is going to be cos 2 pi 3 times f naught t. Then I'm going to keep, you start plugging in the value. So next you try 4. So this is going to be sine of 4 pi by 2. So that would be what? That would be 0, isn't it? This is just 2 pi. And what is sine of 2 pi? So sine is 2 pi is actually 0. So the 4th component will not be there, then the 5th, and then the 6th, and this is how this would look like. Cos 2 pi 5 f naught of t, and so on, all the way up to infinity. This is what you would see. I hope you're getting it, what I'm trying to say here. All right, this is how you would see. This is what the Fourier transform, Fourier series of a periodic signal would look like. That is a rectangular function which is repeating itself like this and continuing itself. All right, this is the Fourier series. Now, if you were to look at it, Now, and then you need to add up all the way from n all the way up to infinity, and you just keep adding the harmonics, the shape. I mean, you're getting more and more component. You will see the sharper the shape is, the more components required for you to generate this type of a signal. All right, so this is how it looks like. So in your time domain, if you were to look at this particular signal in frequency domain, so this, just like you've been seeing it in your textbooks, uh, in frequency domain, this is what my signal looked like, isn't it? Sorry, this looks like. Now, what this would look like is this. You will have a fundamental component, which is there. This is going to be your frequency. This is going to be a fundamental component, F naught. The next component that you will encounter, that will have 1/3 of the amplitude. The 1/3 of the amplitude is going to be 3F naught. The next component you will encounter that will have 1/5 of your input, that would be 5F naught. As I hope you're seeing the pattern. The pattern would be, next component would be 7F naught, next would be 9F naught, and so on. So the signal that we actually eventually looked at first was actually a periodic signal, and that signal was a symmetric signal, isn't it? So when I had a symmetric signal, and when I calculated a Fourier series of it, I am getting hard harmonics. All right. So if I have a symmetric, so this is something for you to remember, and you can just, if I have an odd signal, which is symmetric along the borders, sorry, even signal, then in frequency domain, this is what I would see. This is what I'm seeing. This definition, this equation is actually showing me a signal that looks like this. That this will have some fundamental component, which is going to be an actual frequency. Let's say if it's 1 kilohertz, then the next is 3 kilohertz, then 5 kilohertz, 7 kilohertz, and 9 kilohertz. And this is what you would see. You would see an individual component, because we know a square wave is made up of a lot of sinusoidal and cosinusoidal components. All right. So I hope you like this small tutorial on how to compute Fourier series of a periodic signal. Very important. If you have any questions, leave it in the comment section, and don't forget to subscribe to my channel.